All right, and welcome to Chapter 20 of, and our final chapter of the semester for Gen Chem 2, and this is going to be on electrochemistry. So this is going to be a pretty slick chapter because we get to start to talk a little bit about how differences in energy levels between electron transfer processes are motivated by reduction potential, and conversely, how these processes can be harnessed to generate electricity. So this is a pretty complex chapter, but it's a really nice way to start pulling together concepts from our first semester Gen Chem and the entirety of what we've been working on in second semester as well. So let's see if I can. So electricity and chemistry. I'm going to keep this pretty straightforward. Electricity is moving electrons, and this is what constitutes electrical current. Chemical bonds form from transfer of electrons, and from breaking. Breaking bonds is also transfer of electrons from one nuclei to another. So what we're really looking at when we're discussing current and voltage and electricity on a macro scale can be isolated down to a micro scale of what's happening between bonds, between different components of a chemical reaction. And I just find this absolutely fascinating. I hope you do as well. So when we're talking about breaking things down into components, it really comes back to oxidation and reduction of a reaction. And anytime we have a reaction where there's a transfer of electrons occurring from one atom to another, or one nuclei to another, this is called an oxidation-reduction reaction, and we typically refer to this as a redox reaction, just as shorthand. The term redox is used much more commonly than oxidation-reduction, just because of oxidation-reduction being a bit of a mouthful. So it's always appropriate to say redox. Now, remember, what is oxidation? What is reduction? Well, oxidation is any atom that loses an electron is being oxidized. And any atom that is gaining electrons is being reduced. So I like to use the little short cheat phrase oil rig, which I've listed right here. Oxidation is loss, is oil, and reduction is gain, is rig. So oil rig, easy Alaska thing to remember. The important thing to remember is what is gained and was lost is actual electrons, because it's hard sometimes when we're looking at oxidation reduction to remember what's being lost and what's being gained. The term reduction was coined even though it is gaining electrons. When you gain electrons, you are reducing charge, at least positive charge. So and then you're also gaining negative charge. So it's very important to keep everything in perspective on what is being reduced, or what is being gained, what is being lost. Specifically, that refers to electrons as part of the reaction. And as long as you keep that part straight, oil rig will steer you in the right direction all the time. So, final point of this slide, and this is some terms that get a little tricky. If you increase your oxidation state of an atom, this is oxidation. If you decrease the oxidative state or oxidative number, that is reduction for the reaction. Okay, good. So as an example here, we have a redox reaction where we have two sodium that are in solid or metallic form, and we have chlorine gas. And that's going to react to form two equivalents of sodium chloride solid, which is an ionic solid. Now, if we look at the components of this, the sodium is reacting as our reactant, and it's going to form a sodium cation, and as part of forming that cation, it's going to have to release an electron. So this is going to be an oxidation event because it is losing an electron as part of the process going from our reactant side of the reaction to our product side of the reaction. Another way to look at this is that sodium is going from a oxidation state of 0, because it's a neutral solid, to an oxidation state of +1, because it's a +1 cation. So this is another evidence of it being oxidized. Now, if we look at the other half of this reaction, the chlorine gas, which is on our reactant side, the chlorine gas needs 2 electrons, 1 per chlorine, to become chloride anion. So in this case, the chlorine gas will react with 2 electrons on the reactant side, which we're seeing here, to form, as our product, 2 equivalents of chloride anion. Because it is losing electrons, reduction is gain. Reduction is gain because we're going to bond 2 new electrons to the chlorine to form chloride. This is a reduction reaction. Another way to look at it, based on the earlier definition, chlorine is going to go from 0 as an oxidation state to -1. Therefore, it has to be reduction. So what we just did in the previous slide is we took a whole reaction and we broke it down into two different halves. And this is something we're going to formally start introducing now. And this is identifying half reactions of a redox reaction. So anytime we're dealing with redox reactions, we nearly always separate them into 2 half reactions. And that is to identify which side is the oxidation side of the reaction and which side is the reduction side of the reaction. And that's what we did in the previous slide, and we just kind of introduced it to you by throwing it in the deep end in the example. But now let's look at it a little bit more analytically. So when we're dividing these into half reactions, the oxidation half reaction has electrons in the products. So remember, oxidation is gain. So it's going to have electrons in the products. And the reduction half reaction, it's a mouthful to get all these things straight. Remember, oil rig, oxidation is loss. Therefore, I knew that didn't sound right. Oxidation half reaction is going to have electrons in the products because the reactant is losing the electrons, and so those electrons are going to be in the product. Reduction is gain, rig, so the reduction half reaction has electrons in the reactant side. So let's take a look at this reaction as an example below me. Go back. There we go. So in this reaction, which is already balanced, we have 3 chlorines plus 1 iodide plus 3 water on our reactant side produce 6 chlorides, 1 IO3 minus, and 6 protons. So let's break this down into the oxidation side and the reduction side. And the easiest way to do that is to look at the oxidation states of each of the nuclei. So right out the gate, let's start with the reactant side. We have our chlorine. The chlorine is neutral, and we've got just 2 chlorines, so it has to be 0 right at the gate. So each of those chlorines is 0 to begin with. The iodide has a -1 charge, so it's -1. Water is a neutral compound, and oxygens always have -2. So each of the protons in water has +1, and the oxygen has -2. Now let's see what changes. Assign these for the product side and then see what changes. So on the product side, chloride now is -1 charge, so it has to have a -1 oxidation state. IO3 minus is a -1 net for the polyatomic ion. This polyatomic ion has 3 oxygens. Each of those has -2. Therefore, to have a -1 net charge, The iodine has to have a +5 charge. And then we have our 6 protons with each having a +1 charge. So now that we have all of our oxidation numbers assigned for each of the nuclei, let's take a look at the differences. What's being oxidized? Well, what is oxidation again? Oxidation is loss. So we're going to be seeing a loss of electrons. In the case of the iodide, on the reactant side, it had a -1 oxidation state. On the product side, it had a +5. So it's lost 6 electrons. And that's reflected on the oxidation half reaction. On the reduction side, the reduction half reaction, reduction is gain, so we expect to see a gain in electrical charge as reflected by the oxidation number. And then we see that in the chlorine, because the chlorine was neutral, gains 2 electrons, and results in a pair of chlorides which each have a -1 charge. So this is how we would break down identifying the oxidation side of the half reaction and the reduction side half reaction. So you may have noticed in the previous slide as we got to the end of it that that didn't seem balanced. Let's bend back. Because we should be neutral in our total electrons transferred between our reactant side and our product side. And that's exactly true. So what we're looking at with these identified half reactions, oxidation and reduction side, wasn't inherently balanced because we had 6 electrons on one side and 2 electrons on the other. Oop, that's going to be addressed now. So we need to balance redox reactions using a method called the half reaction method. It's a really, really useful way to balance complex redox reactions systematically. What we do is we break it down into 2 half reactions, like we just did previously, one oxidation side, one reduction side, and then we individually balance these 2 half reactions for both mass and charge. Then we add them back together to get an overall balanced equation. So systematically, this is what it looks like. We're going to walk through it. It's going to seem overwhelming, then we're going to do a few examples, and it won't be as daunting afterwards. So first off, step 1, we assign our oxidation states and determine what is oxidized and what's reduced. Then we write our oxidation and reduction half reactions. Following that, we balance the mass of the half reactions. And first we balance everything that is not hydrogen or oxygen. Once everything else is balanced, we balance oxygens by adding waters wherever we need an oxygen, and we balance the hydrogens by adding protons wherever hydrogen is needed. And if the reaction is in a basic solution, we neutralize protons with hydroxides as a final step. That seems silly, but it'll make sense once we start doing it. After we've got everything balanced by mass, we balance the charge of the half reactions by adding electrons. And then we make the number of the electrons in both half reactions the same by multiplying one or both sides by a whole number, which gets them to a common factorial. And then we just put them together, cancel like terms, count everything up to double check, and we're good to go. So let's see what this looks like. This is an animation. Here we go. So, let's balance this half reaction as an example. And we have aluminum plus copper ions react, forming aluminum cations plus solid copper. So, step 1, assign our oxidation states. Well, solid aluminum is going to be neutral, and aluminum cations are going to have a +3 charge. So right out the gate, we know that's going to be oxidized because oxidation is loss, and that aluminum is losing electrons going from the reactant side to the product side. Conversely, we have our copper cation, +2 per copper, going to solid copper, which is neutral, so it's 0 charge, and it's going to be gaining electrons. So that's going to be reduction, because reduction is gain of electrons. now that we know what side's what's oxidation and what's reduction, we can split these into half reactions, which we see in step 2 here, where our oxidation side is going to be solid aluminum reacts to form aluminum cations with +3 charge, or aluminum 3, and the reduction side is going to be copper 2 cations reacting to form solid copper. Step 3 of this, we have to balance each half reaction with respect to mass. In those following orders, we do everything that isn't hydrogen or oxygen, and then we balance with oxygens and hydrogens. But in this particular case, we don't have any hydrogens and oxygens on either of our half reactions, so all we have to do is balance our non-hydrogen and non-oxygen compounds. Thankfully, in this example, everything's already balanced, because 1 aluminum per side, 1 copper per side. So all of our masses are already balanced. So step 4, don't worry, we'll do an example where they're not next. Step 4, we need to balance each half reaction with respect to the charge, and this is done by adding our electrons, because before we didn't have electrons on each side. So for our oxidation half reaction, aluminum reacts to form aluminum 3 cations, but to balance the charge, since this is neutral on the reactant side, on the product side it has to be neutral, so we need 3 electrons to balance that +3 charge. On the reduction side, we have to add 2 electrons to the reactant side to make the reactant side neutral. So it's 2 electrons plus copper 2 cation form solid copper as a product. Now, those are neutral and balanced electrically. However, now we have to make the number of electrons on both of the half reactions equal, because we can't have 3 electrons on the products and 2 electrons on the reactants, because then our net reaction would be charged, and we have a conservation of charge in these reactions. So we have to find a way to balance it, and the easiest way to do that is find the lowest number that both of these terms will multiply into. So we have a 2 and a 3. Well, both of those go into 6. So I'm going to make everything 6, all the electrons 6, and to do that, I need to multiply everything on the oxidation side by 2, and everything on the reactant side, the reduction side by 3. And that will give us 6 electrons on both sides of the reaction, and we'll keep everything else balanced as well. So that's what we've seen here in step 5. And you have to multiply everything by 2. So 2 aluminums, 2 aluminum 3 cations, and 6 electrons. And that's what we're seeing here, 2, 2, and 6. And then we do it again for the copper, and we end up with 6 electrons, 3 copper 2 cations, and 3 coppers. Now, we're in a position where we can add everything together, because our masses are balanced, our electrons are balanced, and our charge for the entire reaction is balanced, and we're in a position where things can cancel when we add these back together. So here's what it looks like. We're going to add them back together, and in this case, we have 6 electrons on the reactant side, 6 on the product side. Those are going to cancel with one another, but nothing else cancels. So the overall balanced reaction is 2 aluminums plus 3 copper 2 cations in aqueous solution react to form 2 aluminum 3 aqueous cations plus 3 copper. And then you just double check everything to make sure it's balanced. Both sides we have 2 aluminums. Both sides we have 3 coppers. Both sides we have a total of 6 charges. You're like, where are those 6 charges coming from? 3 times 2 is plus 6. 2 times 3 is plus 6. And we're set. So, for an analogous type reaction, I recommend pausing the video and working through this example problem below, where we have protons in aqueous solution reacting with chromium to form hydrogen gas plus chromium 2 cations. Go ahead and give it a shot. And then as soon as you're done, let's move on to the next example. And here's the next example. Let's balance this following redox equation. And this is going to be in an acidic solution. So We have our iron 2 cations in aqueous solution reacting with aqueous permanganate, MnO4-, and this is going to react forming the products iron 3 cations and manganese 2 cations, both in aqueous solutions. Right out the gate, what do? Well, we have to identify what our oxidized species are and our reduced species and break out half reactions. And that's what we're going to see right away. Iron's a great place to start because iron is going from its +2 state to its +3 state. To do that, it has to lose an electron. Oxidation is lost. Therefore, iron is being oxidized with the reaction as drawn, going from products to reactants. Conversely, what are the oxidation states of our manganese? Well, in permanganate, MnO4-, oxygens are always -2. Our overall for the polyatomic ion is -1. That means that we have a net -8 charge from oxygens, and our net for our overall polyatomics -1. Therefore, our manganese has to have an oxidation number of +7. Well, on the product side, the manganese has an oxidation state of +2. Therefore, we are going to be gaining 5 electrons per manganese, and that's going to be reduction because reduction is gain. So we can draw these out as unbalanced half reactions without electrons, where we have our oxidation side with our iron 2 going to iron 3, and we have our reduction side with our highly oxidized permanganate going to the more reduced form of manganese 2. So what do we have to do then? We got to balance all of our masses. And in this case, we do have some things that include oxygen and hydrogen to balance. So first thing we need to do is balance everything that isn't hydrogen and oxygen. We have 1 iron on each side, not a problem. We have 1 magnesium on each side, so that's not a problem. No balancing required. But in that half reaction, the permanganate has 4 oxygens. So to add our oxygens, we're going to put waters on the product side because we have 4 oxygens on our reaction side and we need 4 oxygens on our product side. Now that we have balanced our oxygens, we have a surplus of hydrogens on the reactant side because we have 4 times 2 hydrogens on the reactant side. This is 8. So to balance that out, we're going to put protons back on the opposite side in the form of 8 protons. And now we're mass balanced for an acidic reaction. And now that everything's mass balanced, we have to balance our number of electrons on each side. Because iron was a single electron transfer going from iron 2 to iron 3. However, 5 electrons were transferred going from permanganate to manganese 2. So we're going to have 1 electron as a product on our iron transfer, and in our manganese transfer we're going to have 5 electrons as a reactant. Right at the gate you're thinking, okay, well our masses are balanced, but we can't add these together yet because our charges aren't balanced. And you are correct. We're going to need 5 equivalents of our top reaction here to balance 1 equivalent of this bottom reaction. And that's what we're going to have to do here. So 5 across the board times everything is going to give us 5 iron 2s, are going to produce 5 iron 3s and 5 electrons. And now our electrons are balanced on both sides of the equation, and our masses are balanced on both sides of the equation. So let's cancel these bad boys. Add them up and cancel things. Stacked up, we can see our electrons neatly cancel, as they should. If they don't, you weren't balanced. And then we can add everything else together, and you can see our final reaction is displayed below, where 5 iron 2s plus 8 protons plus a permanganate will react to form 5 iron 3s, 1 manganese 2, and 4 equivalents of water. Whew, nice. And nothing here is that complex. It's really not. If you just follow this systematically, you're going to get to the right answer overwhelmingly. Oh yeah, and then we have to double check. So if we were to go back here, we would see, are our irons balanced? Yes, we have 5 irons apiece. Are manganese balanced? Yes, we have 1 manganese on each side of the reaction. Are our number of hydrogens balanced? We have 8 protons on the reactant side. We have 8 protons on the water side. And what about oxygens? We have 4 on each side. Excellent. What about net charge? We could do the same. And this is what it would look like, plus 17 charge per side. So this was a little bit more complicated than the previous example, and I would challenge you guys to take a break from the slides, slow the flow of new information because we're about to start adding new things, and take a second to just run one more practice problem here. Balance the redox reaction for the acidic solution of solid copper reacting with NO3- to form ionic copper in NO2 gas. Go ahead and give that a shot. Take a few minutes, work through it, let that LTP form, and then we'll jump back into the slides. And here's the next slide, electrical current. So, like I said, we're going to start adding nuance, adding a little bit more character to this. So, we can harness these redox reactions because electrons have to flow from one thing to another to undergo a redox reaction. Well, if you make those electrons flow through a conductor, whether that's a metallic conductor or an ionic solution, you can harness that as electrical current. And the motivation of electrons to flow is very analogous to water flowing downhill or a ball rolling downhill or any other demonstration of physical potential energy, except this is electrical chemical potential energy. And just like a steep, tall hill will let something roll faster and further, a larger difference in redox potential between the reactant and the product will determine the motivation for electrons to move. And this is just an example of ions moving in solution as part of a redox reaction. So in this particular case, we have a strip of solid zinc that's immersed in a copper 2 sulfate solution, and we get a transfer of electrons where the solid zinc transfers its electrons to the aqueous copper, forming solid copper on the surface of the electrode and dissolving the zinc from the electrode into solution. So, a couple things terms we have to get out right out the gate, because we're talking about electricity, is what are some of the ways we measure electricity. And current is going to be our first term. It's the number of electrons that flow through the system per second. And the term which we use to measure current is an ampere or amp, which is a capital A. And an amp of current is 1 coulomb of charge which flows per second. And the number of electrons that is equivalent to is 6.242 times 10 to the 18th electrons flowing per second as part of a reaction. So that's going to be 1 amp. The potential difference, what I was referring to between the reactants and the products in terms of the potential energy, that redox energy, is going to be determined in volts. Oh, you say, I know what volts are, because, a socket is 120 volts inside a house, roughly. Car batteries are roughly 12 volts. Well, what do volts mean? Well, volts are just a measure of potential difference between reactant side and product side in an electron transfer reaction or redox reaction. What a volt physically is equivalent to is 1 joule of energy per coulomb of charge. So higher volt means that you get more energy per coulomb of charge moved because of the delta between the reactant side and the product side. And this determines the electromotive force, or the force that's pushing the electrons through a circuit, or you can think of it as the force that is driving a chemical reaction to occur. So higher voltage, more electromotive force, also means greater propensity to drive a chemical reaction in a spontaneous fashion from the reactant side to the product side. And we can measure this in an electrochemical cell where we have divided anodes and cathodes, like a voltaic cell, and this is going to be called cell potential. So often cell potential is going to be measured in volts, and we're going to be able to actually measure, experimentally determine the potential of half reactions compared to reference reactions, but we'll get there in another slide or 3 or 4. And remember, once again, the cell's potential depends on the ease or propensity with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode, because these are two separate half reactions that are divided into cells. Or you can also think of it as cell potential being what is the difference between the reduction half reaction and oxidation half reaction. Now, we can categorize this under standard conditions, of course, with standard EMF or the reduction potential or the standard potential for the cell. And this is going to be at 25 degrees Celsius, 1 atmosphere for gases, 1 molar concentrations of solution for aqueous components. So, quick summary of what constitutes electrochemical cells, then we'll start jumping into these cells. Oxidation and reduction half reactions have to be kept in their own half cells. If they're mixed, you can't harness the transfer of the electrons through wires or through an ionic solution. So you have to keep each half reaction in their own half cells. The electrons are going to flow between these half cells through a wire, and then ions are going to flow through the solution, and this is going to give us an electrical current, which we can actually harness and measure. This process is going to require a conductive solid electrode, which allows for the transfer of electrons, and this is typically graphite or metal. And it also requires ion exchange between the two half cells, which requires an electrolytic solution. So this is what it looks like. We have our 2 electrolytic half cells. On one side we've got our oxidation cell with zinc being oxidized, and on the other side we have our copper cell, which is being reduced with its half reactions. And we have anode on the oxidation side, cathode is our reduction side, and electrons are going to move from the anode to the cathode, and the voltage is going to be determined by the difference between these two. Notice we are connected by a wire to move electrons across, and we have this salt bridge, which has these little glass wool plugs on the ends of the bridge, but it's full of electrolytic solution as well, which allows anions to move across and maintain ion neutrality as well during the reaction. Okay. So, I already mentioned anodes and cathodes, but super important to keep these identities straight in your head. The anode is the electrode where the oxidation occurs, and it's going to be the more negatively charged electrode in the voltaic cell. The cathode is where the reduction occurs, and it's going to be positively charged. So just make note cards. Anode, oxidation, negative. Cathode, reduction, positive. Keep these identities straight, please. Drill them. You're going to want to keep those straight in your head. Pause. Take a moment. Repeat to yourself. Anode, oxidation, negative. Cathode, reduction, positive. So typically, anode is going to be made of metal, and it's going to actively be participating in the oxidation process. And the cathode is going to be made of the same metal as is produced by the reduction. That's what's typical. Occasionally, if the redox reaction involves the oxidation or reduction of an ion to a different oxidation state, or the oxidation of reduction is a gas, we might use inert electrodes. So an inert electrode doesn't participate in the reaction, but just provides a surface for electron transfer as part of conduction. But typically, you're going to see examples where anode is made of the metal being oxidized, and the cathode is going to be the metal that's being produced by the reduction of an aqueous ionic component. So, notations, there's a nice way to denote the construction of these cells with shorthand, and you always write the oxidation half cell on the left and the reduction half cell on the right, and you separate them by two vertical lines. So that's going to be your separation of your two half reactions. And then substances in different phases are separated by a single line, which represent boundaries between phases. So, example, solid phase, aqueous phase, going to get the single line. And if you have multiple species in the same phase, you just use a comma between them to show that they're all in the same phase. You don't throw in another single line. And you can also include an inert electrode in this. So you can also think of the double line as your salt bridge, if you're so inclined. So if you look at this final bullet, the easiest way to set up these fast is to have your electrode followed by a single line, followed by your electrolyte, followed by your double line, followed by electrolyte on the other reduction half cell, followed by your electrode on your reduction cell. So remember, first side is ox, second side's reduction. And this is an example of this type of reaction being denoted in shorthand. On the oxidation side, we have aqueous iron as an electrolyte and an iron anode. And then we have in the reduction side, we have our free protons because it's acidic. We have manganese 2 and permanganate. And then our cathode is going to be platinum. And this would be an example of an inert electrode. Because the platinum is not participating in the reaction, all of the electron transfer is taking place between the permanganate and the manganese. But the cathode is picking up those electrons and coming in from the anode side and releasing them to the solution to allow for the reaction to take place. So to draw this out, we'd start with the oxidation side, which would be our anode, iron solid, our electrolyte solution, iron 2, aqueous, double line, permanganate, comma manganese, comma protons, all aqueous, line, platinum electrode for our cathode electrode. Now, what are we referencing when we're talking about magnitudes of voltages? Well, we can't really determine an absolute tendency for half reaction, so we have to reference them off of something. So arbitrarily, what's been selected is the use of the half reaction for the reduction of protons to hydrogen gas. And this is called the standard hydrogen electrode. And the standard hydrogen electrode has been assigned a voltage of 0 because it neatly falls between an array of reactions, and it also is fairly easy standard to produce. So this is what 0 voltage in terms of standard reduction potential looks like. And everything else is voltage, whether it's higher than that or lower than that, is determined based on this reference. So Let's take a look at some of these cell potentials. Remember, potential is just like potential energy. If you pick up a ball higher, it has more potential energy. And the same is true for electrons. The more the potential for the electron to move from one place to another, the greater the motive force, the greater the tendency for that to occur, the more likely that reaction will occur. So a half reaction with a really strong tendency to occur is going to have a really positive half cell potential. When two half cells are going to be connected, because we're not talking about half cells in a vacuum, we're talking about how these half cells interact with one another, the electrons are going to flow so that the half reaction with the stronger tendency occurs. It's a tug of war. Even though one half reaction may have a fairly strong tendency, if it's interacting with another half reaction with an even stronger tendency, the one with the stronger tendency is going to occur. This is like describing weak acids behaving as bases in the presence of much stronger acids. Just like acids and bases are a relative thing in terms of the way they behave relative to one another, potential is the same way. So in this particular example, we have an anode with a solid zinc losing 2 electrons and becoming a zinc 2 cation. And we have a cathode where it's our standard hydrogen electrode with 0 volts. And you can see that it has a negative 0.76 volts for the anode side of the reaction. Because the zinc, so when two cells are connected, the electrons are going to flow, so the half reaction with the stronger tendency is going to be the thing that occurs. Because this example prefers the electrons move, these 2 electrons transfer from the zinc to the hydrogen, this is going to be a spontaneous reaction. Conversely, if we have a scenario like we see here, where the anode side has a positive voltage as compared to the reference electrode, if we hook this up as 2 coupled half reactions, it will be non-spontaneous for the 2 electrons to move from this case copper to the hydrogen, because there just isn't the same motive force. It has a lower voltage than the reference electrode. So those electrons just don't want to move to form that reaction. And you can see that from the delta here between the two. Now, I mentioned briefly in a previous slide that we could use a reference electrode to determine the voltage. Well, because our reference electrode is always going to be 0 volts, if we are measuring through a voltmeter 2 half reactions, the difference between these two is going to be equivalent to what is happening on the anode side. So if we use our hydrogen standard electrode, or standard hydrogen electrode, as our cathode, we can always find out what our anode's half reaction voltage is, whether it's positive or negative as well. I think everything we've talked about covers the first couple points here. Here we go. Starting on the 3rd bullet. Half reactions with stronger tendencies towards reduction than a standard hydrogen electrode are going to have positive values for reduction potential, for our standard reducing potential. Half reactions with stronger tendencies toward oxidation than the standard hydrogen electrode are going to have negative values for their reduction potential. And remember, reduction potential is a measure of how something wants to be reduced. And reduction is gain of electrons. So if it has strong tendency towards reduction, that means it wants electrons, and it's going to have a positive value for standard reduction potential, indicating it wants those electrons. If it wants to be oxidized, that means it wants to lose its electrons. Therefore, it's going to have a negative reduction potential. So, positive reduction potential means it wants to be reduced. Negative reduction potential means it wants to be oxidized. This is important because when we start looking at our standard tables of reduction potentials for half reactions, it's all going to be listed as reduction potential. And you have to be able to invert between reduction potential and oxidation potential. And the way we do that is by just taking the opposite of it. So if you want to know what the oxidation potential, standard oxidation potential for a half reaction is, you just take the reverse, or the negative of the reduction potential. You can also think of that as, if you want to see the reduction potential for the opposite direction of the reaction, or as drawn, you can do that as well. Now, what's really important is when we're determining the overall standard potential for a cell coupling two half reactions, we have to know which half reaction is the oxidation reaction, which one is the reduction reaction. And the delta between those two is always the oxidation half reaction minus the reduction half reaction. And that will give us, that says call, but it should say cell, the standard potential for the cell. So let's see what that looks like. Oh, here we go. So this is the table I was just talking about, where we have a sequence of increasingly more positive values for these lists of half reactions. And as we go up on this list, you see an increased tendency towards reduction. Reduction is gain of electrons. These reactions, these half reactions as drawn, very, very, very much want to gain electrons. Conversely, as you are at the top of this list, they have a very low tendency towards oxidation, meaning as drawn, they do not want to lose their electrons. And then those are all positives. At the top of this half, we see our standard hydrogen half reaction arbitrarily set at 0. And everything below it has increased potential for oxidation. Now remember, this is looking at reduction half reactions. So a negative value, like we have for lithium here at the very bottom, means it's a terrible reduction reaction, but it's an excellent oxidation reaction. So they have low tendencies towards reduction, but very high tendencies toward oxidation, with those negative reduction values, which are in volts, by the way, as our unit. So let's calculate some cell potentials under standard conditions. So the standard reduction, or the standard potential for a cell, is going to be, my goodness, they got that completely backwards. Okay, so we got the oxidation reduction, so we're going to go cathode anode here. It's going to be our cathode side versus minus our anode side. And this is whenever we're adding our values for our half cells, do not multiply the values for these potentials because they are intensive. You don't have to balance the values. I know that's not intuitive, but if you're doing a reaction between two sides, the impetus for the electrons to transfer is determined absolutely. The number of electrons that can transfer are determined by how balanced the equations are. But the impetus between the two half reactions is an intensive property. So don't balance the values along with the equations. Just use the standard half reaction values. And we've covered this. So let's just do an example. And then we're almost done with this first lecture. And then we have one more to go. So you guys are almost there. So using the standard table that we have a couple slides before, and that you would have available to you, do not have to memorize a standard table. You're always going to have one available or be given the values. Use the standard table, electrode potential, to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees Celsius. So this is all going to be standard conditions. And this isn't a balanced equation, so you don't have to think about balancing it. We're going to have solid aluminum plus NO3 minus plus protons goes to aluminum 3 plus NO gas plus 2 water. So what do we do first? Well, we're going to begin by separating our half reactions into our oxidation and reduction half reaction. And very conveniently, aluminum goes from 0 to 3 plus. Therefore, it has to lose 3 electrons. Therefore, it has to be oxidized because oxidation is loss. And on the reduction side, we're going to have everything else. So then what we need to do is we need to balance our number of electrons. Looking back, we have 3 electrons, 3 electrons. It was already balanced. So we can take our anode side, which is oxidation, look up our voltage for it, for its standard potential. To be reduced, it has a negative 1.66 volts. On the reduction side, on the cathode, we have a standard potential of 0.96 volts. Notice that our electrons neatly cancel, and if we defer back to our equation of our standard potential for cell being the standard potential for the cathode minus the standard potential for the anode, is going to be 0.96 minus a negative 1.66. So this is going to have a nice large potential of 2.62 volts. So remember, minus and minus is a positive. So when we have these negative values, oftentimes we're going to end up with a large positive for our cell. I'd recommend repeating this exact process for the following example. Open up a table, go ahead and crush through this, get it ingrained, make sure it's making sense. If you get hung up, go ahead and maybe review this one or jump to the next problem. Oh, there isn't a next problem, excuse me. So, how do we predict spontaneity of reactions? Well, spontaneity of a reaction is going to mean a number of things, but we're going to start relating spontaneity of reaction. We've already looked at delta G, we've looked at K, and now we need to look at our reduction potential as a tool for determining spontaneity of reaction. So remember, substances listed at the top of our standard reduction potential tables tend to undergo reduction. Because they tend to undergo reduction, they are good oxidizing agents. Substances listed near the bottom tend to undergo oxidation, and that makes them good reducing agents. And any reduction reaction on these standard tables is going to be spontaneous if it's paired with the reverse of any reaction listed below it. So if you just look at where things are on the table, if you take any reduction reaction and you pair it with the reverse of something below it on the table, it will be spontaneous. It's a really slick shortcut when you have these tables. If they're not looking for actual potentials and they just want to know spontaneous versus non-spontaneous, that's how you're going to know. You're going to know that the reaction on top, when paired with a reaction below it, the reverse of a reaction below it, is going to want those electrons more. and therefore it's going to get those electrons and it will be spontaneous. If the reaction's being paired with the reverse of something above it, the one above it has a higher reducing potential. And it's going to want those electrons more, and it's going to not function as an oxidizer. Therefore, the one that you think is targeted for reduction can't get those electrons from that half reaction, and it will not be spontaneous. So, as an example of this, without doing the E-cell calculation, just predict the spontaneity of the following reactions. For A, iron plus magnesium 2 cations react to form iron 2 cations plus magnesium. And you can break this down into the two half reactions where you have magnesium plus 2 electrons forms magnesium metal. You can also look at the oxidation of iron solid to iron 2 plus 2 electrons. If you just go to the tables and look at the standard reducing values for these, you can see a voltage of negative 2.37 volts for the magnesium half reaction and negative 0.45 volts for the iron side of the reaction. Now, is this spontaneous or not? The magnesium half reaction is significantly more negative in potential. Therefore, it is going to repel electrons and wants to undergo oxidation. It's negative, so it's a very poor reducing half reaction. Remember, reduction is gain of electrons. The iron half reaction has much more positive electrode potential compared to the magnesium, and therefore will attract electrons more strongly, and it will be the thing that undergoes reduction. So if we look at the reaction as drawn, iron as drawn is losing electrons. It's the one being oxidized as drawn. So this is going to be non-spontaneous. However, if you drew it in reverse, if we went back, and you looked at it going this way, that would be spontaneous, as drawn, going from reactant to product, for the exact analogous rationale that we just walked through. Likewise, let's look at lead and iron. So we have solid iron reacting with aqueous lead 2, form aqueous iron 2 plus solid lead as products. And this reaction is going to involve the reduction of lead 2, because reduction is gain. So lead 2 plus 2 electrons gives us solid lead, and that's going to have a potential of negative 0.13 volts. Iron, solid iron, in this case, would be oxidized to form iron 2 plus 2 electrons. It's going to have a potential of negative 0.45 volts right out the gate. Which ones are better reducing half reaction? This one, that's the one that wants to gain electrons, right? So, which ones are better oxidized half reaction? This one, because it doesn't want to be reduced. So this is going to be spontaneous as written, because the lead half reaction has a greater propensity to be reduced. Reduction is gain of electrons, and that's what we're seeing here, and it's what we're seeing here. This lead wants those electrons so that it can become neutral, and this iron wants to give its electrons to that lead so that it can become oxidized. Now, if we were to draw this the opposite way, it would be non-spontaneous. So go ahead and try this for the following two examples, and just drill it in And you can think through it in terms of the rationale that I was just talking about, or you can just stick with the rule of if you pair any reaction with something below it, the reverse of something below it, it will be spontaneous. And if you pair it, or attempt to pair it, with something above it, it will be non-spontaneous. Whichever one works easier for you. Or both. And finally, last slide. How do you predict whether or not a metal is going to dissolve in acid? Well, metals whose reductions of their reduction half reactions are listed below that of the standard hydrogen potential will dissolve in acids, because they're going to give up those electrons and become aqueous cations as part of the process, because they are below that of free protons, which want those electrons. So it's just an extension of the rule we introduced in the previous few slides about spontaneity. And taking something from a solid to aqueous will dissolve the metal. So almost all metals are going to dissolve in nitric acid because of this rule. You can dissolve a solid copper penny in nitric acid. It's glorious. It turns green, and then a shade of green-blue, and then blue as the copper becomes oxidized from copper 1 to copper 2. It's a fun experiment to do if you can ever find a pre-1984 penny which is just got tons of copper in it. Or you can just dissolve the copper sheath off of a penny, and that works equally as well. Now, what's fun are certain metals, rare metals that are highly cherished, resist oxidation, but they also resist being dissolved. So things like gold and platinum really resist these processes, and you need more aggressive acids like a combination of hydrochloric and nitric acid to get those to dissolve. But that's just trivia for now. And that's going to be the end of this first lecture. On the next lecture, we're going to jump right back in and keep building on this. One more to go, guys, and then we are in the home stretch. For those of you watching real time, we're going to be entering Thanksgiving week here. Please enjoy Thanksgiving, enjoy your family and friends and loved ones, and as soon as we're done with that, we can get back to reality. I'll talk with everyone later. Bye-bye.